Hello everyone. In this lecture, we are going to study the isomerism in coordination compounds. In our previous lecture, we have studied Werner's theory of coordination compounds. According to Werner, there, there may be existence of isomerism in coordination compounds that we have to see here. The isomerism, the existence of coordination compounds with the same molecular formula but different arrangement of ligands was the crucial in the development of coordination chemistry. The coordination compounds which had same molecular formula but the arrangement of ligands is different. The isomers, which are the compounds which have same molecular formula but different structural formula, and they do not have similar properties. Such compounds are called as isomers. They differ only in the structural formula. There are mainly two types of isomerism. One is called as structural isomerism and stereoisomerism. We will see the classification of this isomerism. The isomerism first is the structural isomerism. This structural isomerism arises due to the difference in the structure of coordinated compounds, that is the arrangement of ligands. Then the second type of isomerism is stereoisomerism. This stereoisomerism is arise due to different spatial arrangement of ligands around the metal ion. Structural isomerism is further divided into four classes, that is ionization isomerism, hydrate isomerism, linkage isomerism, coordination isomerism. The stereoisomerism is also again divided into two classes, geometrical isomerism and optical isomerism. We will see all these type of isomerisms in detail. The structural isomerism. In the structural isomerism, we will see the first class, ionization isomerism. This ionization isomerism is due to exchange of groups between the complex ion, that is coordination pair, and the ions which are outside the coordination pair. Only the position of ions is changing in between the coordination pair and outside the coordination pair. Because of this, we get different ions. Those complexes which have same molecular formula, but due to position of ions inside and outside of coordination pair, we get different ions when they are dissolved in a solvent. For example, this complex pentamine bromo cobalt sulfate, which is red in color, and this isomer is CONH3 5 times SO4, which is in coordination pair, and bromide is outside the coordination pair. If we see the molecular formula of this complex, it is same COBr NH3 5 times SO4, but in the first isomer, sulfate ion is outside the coordination pair and bromide ion is inside the coordination pair. When we dissolve this complex in a solvent, we get sulfate ion and one complex ion, and it is violet, red to violet in color. Its isomer has bromide outside the coordination pair and sulfate is inside the coordination pair. When we dissolve this complex in a solvent, we get bromide ion and one coordination ion. This is the only difference in the formation of ions. That's why it is called as ionization isomers, and the phenomenon is called as ionization isomerism. This is another one example of this ionization isomerism. In first we get nitrate ion, and in second we get chloride ion. Second type of isomerism is hydration isomerism. It is quite similar to previous one, but in this the position of water molecule changes as inside and outside of the coordination pair. As the position of water molecule is changing, that's why it is called as hydration isomerism or hydration isomers. For example, there are three different ions of the molecular formula CrCl3 6H2. In the first one, which is violet in color, there are three chloride ions which are outside the coordination pair, and all water molecules are inside the coordination pair. In its isomer, which is green in color, we have seen that one water molecule is outside the coordination pair remaining as water of crystallization, and one chloride is inside the coordination pair. In second isomer, two water molecules are outside the coordination pair. This remains as a water of crystallization. We call it as hydration. Only the role of water molecule is changing. In the first, all water molecules were ligand. In second, 5 water molecules are ligand and 1 water molecule is acting as a hydration. That's why such type of isomers are called as hydrate isomers, and the phenomenon is known as hydration isomerism. The third type of isomerism is linkage isomerism. Certain ligands contains two donor atoms, but out of these two, only one is capable to donate the lone pair at the same time, at one time. For example, nitrite ligand, which has oxygen, also has lone pair, and nitrogen also has lone pair. But only one time, one atom can donate lone pair, either nitrogen or oxygen. So there are the compounds which are known compounds in which same nitrate ligand, same nitro ligand, in which in first nitrogen is a donor and in another one oxygen is donor. For example, in this complex, in first one nitrite is forming bond from nitrogen to cobalt, that is the nitrogen is donating the lone pair. In the next, its isomer, out of this NO2, oxygen is donating the lone pair. Its molecular formula is same, CONH3 5 times NO2 Cl2. Only difference is that the point of attachment, linkage between metal and ligand. In first one, there is linkage between cobalt and nitrogen, and in second example, there is linkage between cobalt and oxygen. That's why these are called as linkage isomers, and the phenomenon is called as linkage isomerism. Next type of isomerism is coordination isomerism. In this, only the coordination pair of ligands changes. Mostly this type of isomerism is observed in a complexes where both cations and anions are the coordination pairs. For example, this one, platinum tetraamine, platinum tetraamine platinate, tetrachlorocopper. In this first, amines are coordinated with platinum and chlorides were coordinated with copper. But in its isomer, amines were coordinated with copper and chlorides were coordinated with platinum. Only difference is the coordination pair of chloride and amine is changed. That's why these are called as coordination isomers. In next example also, there is change in coordination pair of amine and cyanide. That's why these are called as coordination isomers, and the phenomenon is called as coordination isomerism. Now we will see the stereoisomerism. This stereoisomerism, as its name indicates, stereo, there is the difference in spatial arrangement of groups in space. That's why it is called as stereoisomerism. They have same molecular formula, same structural formula, but the arrangement, direction of groups is different in the space. This stereoisomerism again classified into two classes: geometrical isomers, which either cis or trans, etc., and optical isomers. In optical isomerism, it relates with the optical activity, that is rotation of plane polarized light. We will see these two types of isomerisms in detail. Geometrical isomerism. In a geometrical isomerism, this isomerism arises due to different position of ligands around the metal ion. For example, it may be on same side, it may be on different side, that is, it may be opposite side or it may be adjacent side. Now in case of four coordinated complexes, in the complex, when the ligands are on the same side, that is on the adjacent position, is called as cis isomer, and in the isomer which are ligands are on opposite side, these are called as trans isomer. This type of isomerism is mainly found in 4 and 6 coordinated complexes. In 4 coordinated complexes, the geometry may be tetrahedral or may be square planar. Now, in case of tetrahedral complexes, in tetrahedral geometry, all the 4 positions are equivalent. In those positions, we are not able to differentiate same side positions and opposite side positions. So, in tetrahedral complexes, this cis-trans geometrical isomerism is not possible because all positions are equivalent. In square planar complexes of mx2 L2 type, that is two ligands of same side and two ligands of same type, the cis-trans isomerism may possible. For example, we see this one example, platinum dichlorodiamine platinum. In this, in the first, two chlorides are on the same side and two amine ligands are on the same side. That's why it is called as cis form. And in another one, two chlorides are on opposite side on the diagonal of this square, and two amines are also at the diagonal on opposite side of this square. It is called as transform. So such type of complexes exhibit cis-trans isomerism, that is geometrical isomerisms. In the octahedral complexes, such as tetraamine tetraamine dichloroplatinate, it can be prepared in two forms, cis and trans. When the chlorine atoms are adjacent to each other, it is called cis form, while when two chlorine atoms are opposite side is called as trans form. For example, in octahedral geometry, what happens? There is one plane. In that plane is square, and 4 ligands are arranged at the corner of that square, and our remaining 2 ligands, one is above that square and one is below the square. So we may say that all these 4 positions of corners of square are on same side, and the upper position is also on same side and lower position is also on same side. So here in first example, two chlorides, one is on the upper position and one is at the corner of a square. So it is called same side, it is the cis form. Whereas in second one, one chloride is above the plane and one chloride is below the plane, and in between them there is a plane square. That's why this is called as opposite position, and this isomer is called as trans isomer. So such type of compounds, complexes exhibit cis-trans isomerism. In optical isomerism, we will see the such type of isomers has same molecular formula and spatial arrangement of groups. Optical isomers have same molecular formula, same arrangement of groups, but difference is that they rotate plane of plane polarized light in different direction by equal magnitude. Some will rotate the plane of plane polarized light in left hand direction, or may rotate in another isomer rotate plane of plane polarized light in right hand direction. So only difference is in the rotation of plane polarized light. The complexes which rotate plane of plane polarized light in clockwise direction are called as dextrarotatory, represented by small d form, and those rotating in anti-clockwise direction are called as levorotatory, denoted by small l form. Or dextrarotatory may be represented by the plus sign, and levorotatory may be represented by the minus sign. Now, if we take mixture of these two, D form and L form, equimolar mixture, then the net rotation of plane polarized light is 0, because if we take two molecules, one is of D form and one is of L form, D form rotates light in right hand direction, whereas L form rotates plane plane of that light in left hand direction. The net rotation is 0. So in such case, if we take equal mixture, equimolar mixture of these two isomers, then there is no optical activities observed, though they have optical centers. Now such mixture is called as racemic mixture. These optical isomers are found in tetrahedral or octahedral geometries, whereas square planar complexes do not exhibit optical activity because they are planar. They have some elements of symmetry like plane of symmetry, axis of symmetry, etc. So the optical isomerism in square planar complexes is not possible. Only tetrahedral and octahedral complexes can exhibit the optical isomerism. The cobalt NH3 ClBrI, in this complex, this it is a tetrahedral complex. All four ligands are different. One is iodide, another is bromide, another one is chloride and amine. Such complexes can exhibit optical isomerism. Now one more condition is that in that optical isomers, these two isomers should be mirror images of each other, non-superimposable mirror images of each other like our hands. Okay. So the enantiomer, that is called as enantiomers, optical isomers are called as enantiomers. So these are the enantiomers are the non-superimposable mirror images of each other. So in this case we have shown the two isomers, we may call it enantiomers of this complex, and these are exact mirror images and these are non-superimposable also. In case of octahedral complexes of MAA thrice type, means there are three bidentate ligands can exhibit optical isomers. This means that many octahedral tristillates, whether with a symmetrical or unsymmetrical bidentate ligands. Ligand may be symmetrical, may be unsymmetrical. In this case, we have taken the symmetrical ligand AA. It is a bidentate ligand. AA means bidentate ligand which have same donor atom. For example, tris ethylene diamine cobalt. In this, optical isomers are possible, and this is shown in this way. See here, this L form and D form, both are mirror images of each other, and these are non-superimposables also. So in this case, we may say the optical activity. In this way, the isomerism is possible in coordination compounds. Thank you.